Good morning and or afternoon. Hello, how are you doing? Welcome. We're going to talk about differentiation, make it real quick and easy. But before we go, let's start with a joke. What do you get when you combine a rhetorical question and a joke? All right, let's get into it. If you didn't laugh, that means you didn't get it. Unlucky. Okay, so today we're talking about the rule for differentiating powers with x. I believe that you've already slightly seen this. But I'm just going to go over it and go over a couple examples as well as the notation. So if fx equals x to some power of n, your f dash x simply becomes n. So the power comes down the front, your x kind of remains, and then you take away one from your power. All right, that's the general rule that we start to use, and this is going to become your bread and butter for calculus. All right, so remember it, practice it, do lots of questions. Now, in terms of the notation, if your original function is fx, then your derivative version will be f dash x. Kind of makes sense. Now, y, if you want to be lazy, you can just do y dash. That's the differentiated version of y. But later on, you will start to see this kind of notation, dy dx. Now, that means f dash x, y dash, dy dx, they are all kind of like, they mean the same thing. They mean a derivative, a derivation, a derived version, whatever you want to call it. That's what that is. Okay, cool. In terms of the dy dx, just really quick, it just means that you're differentiating y with respect to x. That's why it's dy over dx. Okay, you'll see how that's more important later on. But here we go. We've got differentiate. Let's do a couple of these ones here. I'm going to smash out these examples. And if you know what, if you're confident, pause the video now and actually attempt these before I go through them. Okay, now I bet you didn't pause. Maybe two of you did. If you did, good job. Okay, so if I've got f dash x here, power comes down the front, and then you take away one from the power. So 3 take away 1 is 2, 3x squared. For this second one here, f dash x, you're going to have 2. The power of 2 comes down the front, so 4 times 2, that gives me 8. X, and then 2 minus 1 is just to the power of 1, but I really don't need to write that. So it's just going to be x to the x, 8x. Okay, now, the reason I wanted to do these next two, why is my dog like this? It's 6:30 in the morning. It's fine. Let's power on. I can see that you guys can hear him. Okay, f dash x. For this one here, if I have just a singular power of x, what happens is it just becomes 10. So because the power is secretly 1, 1 times 10 is 10, and then x to the power of 0 becomes, I guess, just 1. So it's 10 times 1, it's just 10. The x will disappear. Okay, and if you have a number that doesn't have an x, notice how it's missing. There's no x's, so that means if you differentiate this, it actually just becomes 0. It just, poof, disappears. Okay, so if we've got a question here that kind of combines all these different things together, let's just go term by term. So let's differentiate the first term. That becomes 2 times 3, which is 6. Take away 1 from the power, that becomes 6x. If I've got minus 2x here, that's just going to become minus 2 because the x will disappear when I differentiate. And then that 3 also completely disappears. So 6x minus 2, that's my derivative. Okay, hopefully that's making sense. I'm going to move on. Oh, there's one more. Okay, if you've got a question like this, where you've got some sort of, I guess, product, we can't really, well, you'll learn later that you can, but for the time being, what you'll need to do is you'll need to expand this guy before you differentiate, right? Because these ones here, you can only differentiate when all the terms are kind of like separate. Here, they're multiplying, so we need to expand that out. So this will come x to the power of 3, take away 3x squared, and then now we can differentiate. So f dash x is going to become 3x squared minus 6x. And there you go. That's it. Now, again, this thing, think of this as though this is going to be your plus and your minus, and this is going to be like almost the foundation of everything that you do from now on. Now, this is just a really quick example of what it's used for. It's used to find the gradient of a curve, and I probably should be a bit more specific. It's the gradient of a tangent, okay? Gradient of a tangent of a curve. Okay, gradient of a tangent. So for fx equals to x squared plus 12x minus 3, find where the tangent has a gradient of 22. So if we're talking about the tangent, I'm immediately thinking f dash x, okay? And that's going to be 2x plus 12. And I want the gradient of the tangent, I want that to equal to 22. So if it's asking for where, I'm going to be solving for the x. So here is just 2x minus 12 on both sides equals to 10. X will equal to 5, if I did that correctly. Yeah. Hopefully that's making sense. So where, when x equals 5, my tangent is going to have a gradient of 22. All right, now find where the tangent again. Tangent has a horizontal gradient. Okay, now I'll write a little note here. Horizontal gradient. If something has a flat gradient, it just means it's a gradient of 0. Okay, so if it's positive, it's going to go up this way. If it's negative, it's going to go down that way. If it's 0, it's going to be flat. Oh boy. Okay, so horizontal gradient. So in other words, we still know that our f dash x, just going from the last question, we still know it was 2x plus 12. If I want a horizontal gradient, I'm going to let it equal to 0 this time. And now we just solve. So 2x will equal to minus 12. X will equal to minus 6. And so that, my friends, is where your tangent will have a horizontal and flat gradient. And you'll find that that's a really important one, finding a horizontal gradient. All right, that's it. Keep it short and sweet. That should be more than enough for your exercise. Enjoy, and I'll catch you guys later. All right, bye-bye.